Today we will discuss on sheet metal operation. Before starting the sheet metal operation, I am showing you the video of an animated video of a sheet metal operation. Here you can see this one is a punch and this one is a die and this is a sheet. So punching, in this operation you can see that the punch is applying the force on the sheet metal, and as a result the shearing action is taking place, and after the shearing action there is a fracture taking place. As a result, this part is getting separated from this sheet. Now in sheet metal operation there are two types of operations. One is the punching, another one is the blanking. When after the sheet metal operation or after the shearing operation, if this one is our desired product or this one is our final product, then we will call this process as a punching operation. And if this sheet, if this disc or this blank is our final product or the desired product, then we will call this operation as blanking operation. So depending on the requirement of the product, we will call it as a punching operation or we will call it as a blanking operation. Now if we see this one from the front, then how it will look like? So this one is the punch and this is the sheet, and the sheet is getting sheared, and then we are getting the final product. Now you can see here that during the process there is a clearance is provided between the sheet, between the die and the punch. Now it will depend on whether it is a punching operation or it is a blanking operation. Depending on the operation, we will provide the clearance either on the punch or on the die. So here you can see that this one is a punch, and on the punch there is a blanking force is getting applied, because this force is required for the shearing action, and this one is the die, and there is a clearance is given. So if we see its schematic view or if we see its the view from the front, then this type of sectional view we will get, where this one is a guide plate which is used to hold the sheet metal. So that's why some holding forces are applied. And this one is a punch. This one is the sheet whose thickness is T, and this one is a cushion given, which is given for applying some counter force. And this one is the die. So you can see there is a clearance provided between the punch and the die. Now whether the clearance will be provided on the punch or on the die, it will depend on whether it is a punching operation or it is a blanking operation. Next, generally with the help of sheet metal operation, we basically convert the raw material into the desired product. But in sheet metal operation, while we convert the raw material into a desired product, there will be no change in the mechanical properties. So basically the mechanical properties are not getting improved. But in the forging operation, you have seen that in the forging operation, while the conversion taking place from the raw material to the final desired output, the mechanical properties are generally improved. Okay, but in case of sheet metal operation, the mechanical properties are not get changed. Now this sheet metal operations are generally used in the aerospace or in the automobiles industries, because in those industries there are needed to fabricate the frames of the automobile or the aerospace vehicles. So in that case, the aluminium is used and titanium is used due to their strength to weight ratio, as well as these aluminium and titanium materials are generally given specific shapes with the help of the die and the punch. Okay, so that is the major application of the sheet metal operations in these industries. Next, coming to the punching operation. So in the punching operation, as I told you earlier, that while the sheet is our final product, then we will call it as a punching operation. But when the disc or the blank, is our final product or our desired product, then we will call it as a blanking operation. So in case of punching operation, the disc is not required. So this is our final product. But in case of blanking operation, the sheet is not required. This disc or the blank is required. This one is the top view of the blank or disc. This is the front view of the blank or disc. Similarly, this is the top view of the sheet. This is the front view of the sheet. Now, in case of punching operation, as I told you that the clearances are provided in punching and blanking in both the cases. So if I write that in case of punching operation, the useful part in case of punching operation, useful part is the disc, or in case of punching operation, the useful part is the sheet. But in case of blanking operation, the useful part is the disc, or we will call it as blank. Okay. Similarly, now we need to provide the clearance. Now, in case of punching, where we will put the clearance, and in case of blanking, where we will put the clearance. Always we need to remember that in case of punching, the punch will have the exact dimension. The punch will have the exact dimension. There is no clearance given in the punch in case of punching. So punch will have the exact dimension. Okay. Similarly, in case of blanking, die will have the exact dimension. The die will have the exact dimension. You just have to remember this one. So you can easily figure out where we have to put the clearance. So as in case of punching, punch will have the exact dimension. So we need to provide clearance on the die. So on the die, the clearance will be given. Clearance will be given in case in die, but when during the punching operation. But in case of blanking operation, just the opposite thing. In the blanking operation, we will give clearance on the punch. Clearance given on punch. Okay. The clearance will be given on the punch. Okay, so in this way you need to remember where you have to put the clearance. So we just have to remember that in case of punching, punch will have the exact dimension. Okay. In case of blanking, die will have the exact dimension. Okay. So in case of punching, if the punch will have the exact dimension, then whatever the whole of the size we want to produce, what are the whole of the size we want to produce, that size will be the size of the punch. So the punch size will be the size of the hole. Size of the hole will be the size of the punch. Okay. Now, as the clearance will be given on the die, so the die size will be bigger than the punch. The die size will be bigger than the punch. That means the die size we can write as the punch size plus. Now we need to provide the clearance. Now the clearance that we provide, that clearance is the radial clearance. So as it is a radial clearance, so we need to put clearance in both the sides. So as we have to put the clearance in both the sides, so we can write it as 2 into clearance. 2 into clearance, as we have to put the clearance in both the sides. And this clearance is basically the radial clearance. This clearance is basically the radial clearance. Okay. Similarly, here the die size is will have the exact dimension. So we can write that the die size will be the size of the blank, because our output is the blank. So size of the blank will be the die size. Okay, that we know. So what will be the size of the punch? So punch size should be smaller than the size of the die. So the punch size will be the die size minus again 2 into clearance, because it is the radial clearance. So 2 into clearance. Okay, so this is, in this way we can find out what will be the dimension of the punch and what will be the dimension of the die in case of punching or blanking operation. So we just have to remember that in case of punching operation, punch dimension will be exact dimension, and the punch dimension will be the dimension of the hole that we need to produce. So as we know that what is the dimension, what will be the diameter of the hole that we need to produce, so we can find out the die. So the die size will be bigger than the size of the punch, so we can find out the size of the die. Similarly, if you need to find out the blanking operation, we know that die size will be exact. So die size will be exact means the die size will be equal to the blank size. So as the blank size we know, so we know the die size, so we can find out the punch size. So punch size will be smaller than the size of the die. Okay, so in this way we can find out the dimension of punching and dimension of the punch and die in case of punching and blanking operation. Now sometimes the clearance are given, sometimes our clearance are directly given as the radial clearance. So sometimes the clearance can be given in the form of radial clearance, as radial clearance. In the form of radial clearance, sometimes the clearance can be given, or sometimes the clearance can be given in the form of with the relation of the thickness and the shear stress, the clearance are given. So sometimes the clearance can be given as that clearance is equals to 0.0032 times the thickness of the sheet into root over shear stress. Okay, where T is the thickness of the sheet, and tau is the shear stress, or we can call it as ultimate shear strength, or we can call it as ultimate shear strength, of the material, material. Okay, of the material. We can write it in this way. So that shear stress, the unit of the thickness is generally in millimeter, and the shear stress unit is given as Newton per millimeter square or megapascal. Okay, and this C will be, okay, this the clearance will be in millimeter, whatever the clearance we will get. Okay, so this is the way how means in this way also you can have to find out the clearance that will be needed. So if in any problem the thickness and the shear stress is given, then you can easily find out what will be the clearance. Okay, and in any problem, if the thickness and the shear stress is not provided, directly the radial clearance is given, then directly you can put that value. Or sometimes the clearance can be given in percentage. Okay, so sometimes the clearance can be given in percentage sometimes. Okay, so it may be written as that the clearance is C%. So C% of what? So basically we should write that it is, the clearance is percentage of the thickness of the sheet. Okay, so in that case the clearance will be the percentage that is given by 100 into T. We can find out the clearance that is required. So in this way we can find out the clearance of the sheet required. Okay, next. Now for the shearing action we will be needed some forces, and that force is called as punching or blanking force. Okay, in punching or blanking, in both the process the forces will be same. Okay, so in punching and blanking operation we have to find out what is the maximum force required during the shearing operation, and this force is given by the flywheel. Okay, so what is the function of the flywheel? The flywheel stores the energy when it is not required, and it provides the energy during the shearing action in the punching or in the blanking process. Okay, so we need to know that what is the amount of maximum force required during this punching or the blanking operation. Now depending on the shape of the blank or the sheet you need to produce, it can be a circular type, or it can be a rectangular type, or it can be a square type. Depending on the shape, you have to find out what will be the amount of maximum force required for the shearing action. So we know that shear strength, or the ultimate shear strength, we can write that ultimate shear strength is the shearing force required by the shearing area, that we know. Now this shearing force required means we can write it as the maximum shearing force which is required, and this area we can write this area as the shearing area, that we know, shearing area. So whatever the profile of the blank, based on that we have to find out this shearing area. Shearing area means, suppose if the profile is a circular profile, then in that case the shearing area will be this portion is the diameter of the hole. So as the diameter of the blank is small d, then what will be its area? Shearing area means this area, which will be sheared. This area which will be sheared. So we can write the shearing area in this case. In this case, the shearing area can be written as, in this case, pi into t into the thickness. So the shearing area can be written as pi into d into t. That is this shearing area, is the area which are getting sheared. So the shearing area in this case will be pi into t into t. Similarly, in this case, the shearing area will be, 2 into L plus B into T. This one will be the shearing area because this is the shearing area. This portion is the shearing area. This portion is the shearing area. So it will be 2 into L plus B into T. That is the shearing area in this case. So if we need to find out the the maximum shear force or shearing force which is required, so we can write that the maximum shearing force that is required in this case, while the profile is a circular profile, in that case we can write it as the ultimate shear strength into the shearing area. Ultimate shear strength into the shearing area. So we can write it as tau into pi dt, that we can write. Similarly, in this case, the maximum shearing force that is required, that can be written as tau into the shearing area, where the shearing area is 2 into L plus B into T. This is the maximum force required to perform the shearing action. So we can see that this is the maximum force that is required for the shearing operation. So this maximum force will be provided by whom? This maximum force will be provided by the punch. Now, as the maximum force will be provided by the punch, so the capacity of the punch must be greater than the maximum force required for punching. Therefore, we can write that the punch capacity must be greater than the maximum force required to shear. Okay, so we can write that punch capacity must be F max into some amount. So what is this amount? This amount is generally, the value of C is generally taken as 1.1 times 1.1 to 1.75. That means we can say that the punch capacity will be needed around 2 times of the maximum force required for punching. So if you can find out that what is the amount of maximum force is required for punching, you can easily find out that what should be the punch capacity. Okay. So in this way we can find out what will be the punching, what will be the punch capacity required. Next, so now we know that what is the amount of punch capacity is required, but we also have to find out that what should be the diameter of the punch, what should the minimum diameter of the punch for the punching operation, and that will be decided by the strength of this material of the punch. Now the strength of the material means generally when the punch is applied, when the punch will apply the force, at that time the punch will experience some resistive force also. So when the punch will apply a force, at that time it will get a resistive force also. So basically in the punch there will be a compressive force will act. Now as the compressive force will act, so we should have to find out the material whose compressive strength will be much more high. Okay, so we know that the compressive strength of a material, we can write that the compressive strength of a material, that can be written as the force that is acting, that force by the area. Now area means which area in this case? Area means this area, because this is the normal load, or we can say it as the normal stress. So as it is the normal stress is acting, so in that case the area will be the normal to the force applied. So normal to the force applied we are getting, this is the normal area. So we can say that if the punch is a circular punch, in that case this area will be pi by 4, and say the diameter is d, so the area will be pi by 4 d square. This is the area. So we can write that the force that will be is called as a compressive load, that will be applied on the punch. This force, or we can write it as the compressive load, which will act on the punch. So what will be the compressive load that will act on the punch? That is the compressive strength of the punch material into the area normal to the applied force. Okay, where sigma c is the compressive strength, is the compressive strength of the punch material, compressive strength of the punch material. Okay, so in this case we can write that the compressive load that is acting on the punch, we can write that the compressive load that is acting on the punch, the compressive load on the punch, this compressive load that is acting on the punch must be greater than the shear load. This compressive load must be greater than the shear load. Then only the punch will not get failed. So we can write that the compressive load means, we can write that sigma c into pi by 4 d square, this one will be greater than equals to the shear load. Shear load, just now we have find out, shear load is the ultimate shear strength into pi d t. So we can find out what will be the minimum diameter required for the punch. Okay, so in this way we can find out what will be the minimum diameter needed for the punch, for this punching operation. Now we also have to find out what is the amount of energy required. Okay, now what is the amount of energy required? How we can find it out? Basically we know that energy that is required, basically we know what is energy. Energy means when we apply any force on any material, what is the amount of movement the material has performed. So that basically that is the work done we taken, and that work done is taken as the energy. So we can say in this case that while we are applying the punching force, in this case if we see, while we are applying the punching force, what is the amount of punch travel is going on? What is the amount of punch travel is taking place? Basically that is the energy required for the punching or the blanking operation. Now say if it is given that this is the amount this is the amount of punch travel must be there. Okay, during the operation, this is the amount of punch travel is needed. Say it is given. That means the punch must move this amount of distance. Let this amount of distance is given as 30% of the thickness. Say this amount is given as 30% of the thickness. That means whatever the thickness is, its 30% is this distance. That means this punch need to move this amount of distance. Okay, now to move this amount of distance, what is the energy required? Okay, and what is the energy required? We will call that energy as the ideal energy. Okay, so we can say that the ideal energy required for punching and blanking, that we can say as the maximum force that is applied, into the punch travel. What is the amount the punch is traveling? That is the punch travel. So we can write that the ideal energy, so we are mentioning it, or we are representing it as energy ideal. So ideal energy required for the punching or blanking operation is the maximum force applied into we will write it as P into T. What is this P into T? Where we can write this P as, where this P is the percentage penetration required for the sheet, to rupture. So this is the amount of penetration is required for the shearing of the sheet. Okay. Now this is our ideal energy that is required. Now suppose there is n number of strokes per minute. So if there is n number of stroke per minute, then we can write that what will be the ideal power that is required. So what will be the ideal power required in this case? So the ideal power will be required as the whatever the energy is required into the number of stroke that is given in stroke per minute. So if I divide it by 60, we will get joule per second, and we know that joule per second is called as watt. So we will get the power as E into N by 60. That is our ideal power required. But in every machine there is a term that is called efficiency. So whatever the power is generated, we don't get that amount of power. So what is the actual power we will get? So to get the actual power, we need to divide the ideal power with the efficiency of the machine. So we will divide the ideal power with the efficiency of the machine. So where this is the efficiency of the machine. Efficiency of machine. Okay. So in this way we can find out what is the actual power is required. Clear? Now suppose there is an numerical is given where you need to do the punching operation. Now while the punching operation, during the punching operation you have found out that you have to punch a 10 mm circular hole and you have to cut a rectangular block whose dimension is 50 by 200 mm from a sheet. Okay, and the thickness of the sheet is 1 mm and the shear stress of the sheet is given as 240 Newton per millimeter square. Now you need to find out what will be the size of the punch, what will be the size of the die, what will be the force required, and what is the energy required for the process. So you can see that you have to find out size of the punch. Now during the punching operation, okay, so initially in the first step you have to perform a punching operation. In the punching operation you have to your final goal is to make a hole which will be 10 whose diameter will be 10 mm. So your goal is, first goal is you have to find out, you have to punch a circular hole whose diameter will be 10 mm. Next goal is you have to form a block, or you have to form a blank which is a rectangular blank and whose dimension will be 50 mm is the width and 200 mm will be its length. So initially if you are asked to find out the size of the punch, so we can divide it into two halves. One is the punching, another one is the blanking. So we can divide it into two halves. One is the punching, another one is the blanking. Before that, as we have to find out the dimension of the punch and the dimension of the die, one thing that is required is the clearance. And we know that how we can find out the clearance. In this problem, clearance is not mentioned clearly. It is given, the thickness is given and the shear stress is given. So we can find out the clearance from that formula. So at first we will find out the clearance first. Okay, so the clearance will be, the formula was clearance is C equals to 0.0032 into T, thickness, in root over the shear stress. Now if we put the values, then it will be 0.0032 into thickness, that is 1 mm, root over shear stress, that is 240 Newton per millimeter square. Newton per millimeter square. So we will get the clearance. The clearance will be 0.04957 mm. This one will be the clearance. Okay. Now after getting the clearance, next we have to find out that for punching, for the punching operation, what will be the size of the die? For the punching operation, what will be the size of the punch and the die? Similarly, for the blanking operation, what will be the size of the punch and the die? So first we are finding out what will be the size, diameter of the punch. Diameter of the punch in case of punching operation. We know what we have learned, that in case of punching operation, the punch size will be equals to the size of the hole. So hole is 10 mm. So punch size will be also 10 mm. We have learned. So diameter of the punch we know. Now we have to find out the diameter of the die. So the diameter of the die, in the diameter of the die, we know that we have to put the clearance. So as we have to provide the clearance in the die, so the die size will be greater than the punch size. So we can write that the punch size is 10 mm plus, now the clearance is the radial clearance. So we will write that 2 into the radial clearance is given as 0.04957. So we will get the size of the die, that is 10.09914 mm. This is the size of the die. Okay, this is the size of the punch. Okay, now we can find out the diameter of the blank also, sorry, the size of the die in case of blanking operation also. So we can write the size. In case of blanking operation, we know that the size of the die will be exact, means the size of the die will be equal to the size of the blank. So size of the blank is 50 by 200. So we can write that the size of the die, will be 200 into 50. 200 is the length and 50 is the width. Okay, this one will be the size, 200 by 50 mm. 200 is the length and 50 is the width. Now what will be the size of the punch? So the clearance is given in the punch in case of blanking operation. So the size of the punch we can write as, we have to give the clearance in both along the length and along the width. So along the width, we can write that the width of punch, will be 50 minus 2 into C. C is the clearance. So if I put the value of C, we can get the value as 49.9086 mm. Similarly, the length of the punch will be 200 minus 2C. So it will be written as 199.9086 mm. Okay, so these are the size we have already get. So we have already completed the size of punch and size of the die in both the cases. Now we are asked to find out what will be the force required. So what will be the force required means, basically we will find out what is the maximum force required for the shearing operation. So the maximum force required for the shearing operation, we know that the maximum force required is the ultimate shear strength of the material into the shearing area. So in this case, what is the shearing area? In this case, the shearing area is pi into d into t, because it is a circular hole. So we can write it as tau into pi into d into t. Pi into d into t. So tau is 240 Newton per millimeter square, that is the tau, into pi into d is, d means the diameter of the punch, so d is 10, into t is the thickness of the sheet, that is 1, So if we multiply it, we will get the value as 7.5398 kilonewton. Okay, actually the value we will get in Newton. So if I divide it by 1000, we will get it into kilonewton. So this is the maximum force required for the shearing action. Similarly, for the blanking operation, the maximum force that is required for the shearing action in this case will be same, tau into the sheared area. But in this case, the sheared area will get changed. What will be the sheared area? In this case, the shear area will be, size of the die. The size of the die is given as 200. So the sheared area we can write as 200 plus, or we can write it as 2 into L plus B. L plus B means L length is 200, width is 50. So 2 into length in plus breadth, length plus width, 200 plus 50 into the thickness. Thickness is 1 mm. So if we calculate it, the tau value will be 240. So we can write it as directly as 240. Instead of tau, directly we are writing it as 240 mm, 240 Newton per millimeter square. So 240 into 2 into 200 plus 50 into 1. So if we calculate it, the value will be 120 kilonewton. So if I divide it by 1000, we will get 120 kilonewton. So you can see in this case we will be needed the maximum force of 7.5398 kilonewton, and in this case we are getting 120 kilonewton. Now you are asked to find out the energy required for the process. Now you are asked to find out the energy required for the process if the percentage penetration is 45.6%. Means for the total thickness, out of the total thickness, 45.6% of the, if the punch moves to the thickness of 45.6% of the total thickness, then the rupture will take place. Okay, so we can find out what will be the energy required. So we will find out the ideal energy that is required. Ideal energy that is required, we can write it as F max into PT. Here PT means P is the penetration. What is the amount of penetration? 45.6%. So we can write it as F max as 7.5398 kilonewton into 45.6 into the width in the thickness is given as 1 mm. The thickness is given as 1 mm. Okay. Now 45.6, it is given in percentage, so we will divide it. So we will get the total energy required for the punching operation. Okay. Similarly, you can find out the energy required for the blanking operation also. Both the processes same. Here also you will just find out F max. You have already found out. You just multiply it with P into T. You will get the energy, ideal energy required for the blanking operation. Okay. So if this type of problem comes in the exam, then you have to solve the problem in this way. Okay, now we are moving to the next portion. Next part is the shear on punch. Now in the shear on punch is basically till our last portion we all discussed that the maximum force required for the punching or the blanking operation. Now if we didn't provide any type of shear angle or any type of shear on the punch, we didn't provide. Now if we provide shear on the punch, then we can perform the shearing action at the lesser amount of force that is required. Okay, so this is the shearing action when the punch doesn't have any shear angle, and this is the shearing action where the punch has a shear angle. Okay, now this is the shear angle given. Now say first we are discussing on this part that when there is no shear, means without shear. So when there is without shear, at that time what will be the maximum force required when there is without shear, and when there is shear given with shear given on the punch, when the shear is given on the punch, then what is the amount of force required as well as what is the amount of energy required. Okay, so basically if we provide shear, okay, so we are writing here, if we provide shear on the surface of the punch, then the shearing force that is required can be reduced. So if shearing force can be reduced, if shear is given on the surface of the punch, Okay, so let's check what is the maximum force required in this case. This is the total thickness of the sheet. And this is the amount that is the penetration required. So we are writing it as P into T, penetration required for the rupture. Okay, so we can write that in this case, what is the maximum force required for the punching operation? The maximum force required, we can write it as tau into pi into d into t. D is the diameter of the punch, so pi into d into t. So the ideal energy required, what we can write? Ideal energy required. So ideal energy required, that can be written as maximum force required into the punch travel, that is P into T. We can find out the ideal energy required when there is no shear in the punch. Now let's find out what is the amount of maximum force required when there is a shear given. Now when there is a shear given, so if I am showing the portion of the punch over here, that when there is a shear given, that means this one is the shear angle given, this angle is the shear angle given, let this is the shear angle, okay, and this is the distance. Let this distance is S, okay, and this distance is say D, that is the diameter of the punch. Diameter of the punch. So we can find out the shear angle as tan theta. We can write it as S by D. We can find out what will be the shear angle. Okay. Now in this case also say this is the thickness. The thickness of the sheet, and here is the penetration required, that is P into T. P into T, that is the penetration required. But in this case, while if you see carefully, while this point will be in contact over here, this point is not in the contact with this point. As a result, this point is basically at a distance of S unit higher from this surface. That means when this point will reach to this depth, basically this part have to travel the distance of S plus this distance PT. That means the punch travel, we can write in this case, the punch travel will be, we can write in this case, will be PT plus S, that will be the punch travel, PT plus S. Therefore, we can write that the maximum force, or we can directly write that the energy required when the punch is with shear, energy required for the punch when the punch is with shear. What is the amount of energy required? F max is same. Okay, so F max is same, so we can write it as F. Okay, and we are writing as F S as F with shear angle. Means the force that we are getting with when the punch with a shear angle, at that time this is the force. I am writing it separately, Fs. Okay, so basically the force required with shear. Okay, so I am writing it as force required with shear. So this is the force required with shear into what is the punch travel? The punch travel will be PT plus S, that will be the punch travel. Okay, so this is the total amount of energy required. Now the energy for the machine is basically same, whether you are using the punch without the shear or with shear. The energy given by the machine is always same. So we can write that now we can write as the energy without shear can be written as equal to energy with shear. You can write it in this way. Energy without shear is equal to the energy with shear. Okay. So we can write it as F max into PT, that will be equal to Fs into PT plus S. We can write it in this way. Okay, or we can write that F is as F max into E into T by PT plus S. PT plus S. Okay, where A is greater than the P and T, P into T. Okay, so we can write, therefore we can write that if S is the force required for shearing with the shear angle is less than the force required without shear, we can conclude that the force required with shear will be less than the force required without shear. Now if we draw it into a graph, if we plot a graph, then suppose in the first case we are plotting a graph. The first case we are plotting a graph. We are plotting a graph where this is the displacement or the punch travel, displacement of the punch, and this is the force applied. Okay, so this is the point when the punch is starting to apply the force. This is the point. Okay, this is the point. So this point is the maximum force. Okay, and this is the contact, first contact with the sheet. Next, it is penetrated up to the punch travel, that is PT. It is penetrated up to a depth of PT. Okay, so when it enters to the depth PT, that is its punch travel. That is its punch travel. That is the punch travel. So this is the amount of work done by the punch. Basically, we can write that this is the work done by the punch, means this is the energy required to shear up to this distance by the punch. Okay. Similarly, if we plot another graph between the force and the displacement, force and the displacement, force and the displacement, okay, so the displacement, and here also when the force, this is when the punch with shear, okay, and here is when the punch without shear, punch without shear and punch with shear. Now here, when the punch will be in contact with the surface, at that time the force that is applied by the punch, that is the maximum force. That is the maximum force. Now in this case, as the shear is provided, we know that shearing force, the force required when the punch with shear, at that time it is lesser than the maximum force. So the force is gradually decrease. The force will gradually decrease in this. Okay. Now, when the punch have to travel, in this case the punch have to travel the distance that is not PT. In this case the punch have to travel the distance as PT plus S. So let up to this point, this is the distance traveled by the punch, that is PT. This distance is say PT. Okay, and then some extra distance the punch have to travel, that is the S. That is the S. So the total punch travel is, in this case, PT plus S. Okay, and this is the work done by the punch. So we can write that if S is very greater, very larger than PT, then we can say that PT plus S, we can say that PT plus S is equivalent to S, we can say, because the PT will be neglected. So PT plus S is equivalent to S, we can write it. So we can say, what are the conclusions we can draw? That if S is the force required for initiating, the force required for initiating the shearing of sheet. Initiating the shearing of sheet with shear on punch. Okay. And what we can write further, that if there is shear on the punch, shear on punch, basically distributes the force over a period of time, right? So shear punch, it distributes the force over a period of time. Okay, last one. That really it reduces the maximum force requirement for shearing. This reduces the maximum force requirement for punching or shearing. Requirement for shearing. Yes, these are the advantage of providing shear on the punch. The next concept, that is the concept of the effective shear. Concept of the effective shear means, suppose the width of the punch, let the width of the punch is very large than the width of the sheet. Say this is the sheet and this is the width of the sheet, and this one is the punch. It is the length of the sheet, the punch, and the width of the punch is very larger than the width of the sheet. So we can write that B1 is larger than B. Okay. So in that case, if we see this one from this side, then we will get a view like this. So we can see that this is the width of the sheet, and the end of the width of the sheet, this is the height, the shear. Okay. Now this is the total shear given. So if we write that, let S be the shear provided on punch. Shear provided on punch. Okay. And B is the width of sheet. B is width of sheet, and B1 is the width of punch. B1 is width of punch. Okay. Now, as B1 is greater than so we can write that S is not the shear acting on the surface. As B1 is greater than B, so obviously this S will not the shear acting on the surface. So say this is the shear S1 which will act on the surface. Okay, so this S1 is called as effective shear acting for the cut. Effective shear acting for the cut. Okay. So when the effective shear concept will come? When the width of the punch will be greater than the width of the blade. At that time, this effective shear concept will come. So what we can write? If we compare these two triangles, this one and this one, if we compare these two triangles, then we can write that S1 by S is equals to B by B1. We can write it. So we can write it as S1, the effect, it will be effective shear acting. It will be effective, not effecting, it will be effective shear acting. Okay, so S1 is equals to S into B by B1, we can write. So for this case, we can write it as for this case, we can write that Fs, the force required, that can be written in our earlier slide. We have written that force required is F max into Pt by Pt plus S. So here we can write that force required is F max into Pt by Pt plus S1, Pt plus S1, right? We can write it, but we can also know that here as the Pt is very small than S, so we can ignore that. So we can write that Pt plus S is equivalent to S. So Pt plus S1 is equivalent to S1. So we can write here as Fs equals to F max into Pt by S1. We can write it as it is very small. It is very small. Okay. So this is the concept of effective shear. So that's it for the sheet metal operation. Okay. So thank you.